Thank you for coming, and I'm honored to have the opportunity to talk at the Black Hat. I'll be presenting about a web-based side channel attack. It enables to identify the social account of a website visitor to an attacker's website. I will also introduce our efforts to mitigate this attack with service providers and browser vendors. My name is Takuya Watanabe, working for NTT, which is a telecommunication company in Japan. And I'm also a PhD student at Waseda University. My research interests are the application security, side channel attacks, and privacy threats for web and mobile users. If you have a question or comment, please do not hesitate to contact me by email or Twitter. And there are 5 co-authors for this work: Eitaro, Mitsuaki, Keito, Takeshi, and Tatsuya. They contributed to designing experiments, inventing mitigations, and writing a white paper. The attack I introduce from now is called Silhouette in some media. Our efforts are summarized in our entity's press release and Twitter's blog, so please check if you are interested. Our research brought 3 major contributions. First, we discovered a new security problem in social web service. Second, we shared service providers with the detail of the attack, and some of them addressed this problem. Third, some major browsers support the same-site cookie attribute, which is a robust mechanism for defending CSAF attack, including our attack. Here, I'll talk about the background of this work. The social web has become ubiquitous in our daily lives. It includes not only popular SNS, but also other forms of services with social features such as shopping, gaming, and dating site. Marketing company reports that internet users have 5 or more social accounts on average. In these services, the accounts can contain privacy-sensitive information. For example, the profile page of SNS often includes real name, face photo, and location data. It can be said that social accounts are linked with variable personal information of users. And in other cases, users may use web services anonymously. When this happens, user posts and user logs may show his secret activities, such as secret screening, purchase history in auction sites, and behavior at a porn site or dating site. Okay, in this work, we demonstrate a practical attack to identify the social account of a website visitor when he holds the login cookie of the service. It can destroy the anonymity of an unknown visitor or expose the secret activity of user by linking the known identity and anonymous accounts. It allows the attacker to do tracking, stalking, social engineering, and blackmailing. Next, I will provide the technical background of 2 fundamental building blocks of our attack. And the first one is the same origin policy, which is one of the most important mechanisms for the web browser security. In this figure, firstly, the target accesses evil.com and downloads JavaScript code. That code forces the target to request to another page of the web service. This is cross-site request forgery, CSAF. Through the request is actually done, the I'm sorry. The request is actually done, but the owner of evil.com cannot acquire that response due to the same origin policy. However, the owner of evil.com can measure the required time of that request. He only needs to compare the time before the request begins and after it is over. We call, in this talk, I call this time RTT in RTT. And I will show the JavaScript code to measure RTT later. And the next one is the most important factor in our approach. Social web services generally have a user blocking feature. If John dislikes Bob or gets into trouble with Bob, he can block Bob through just a button click. When Bob is blocked, he will not be able to see John's profile and contents. Such a feature is implemented in numerous social web services to protect users from spams and online harassment. On the next, I will show an example on Twitter. As in the above, when a Twitter user, John Smith, is not blocking me, I can see his biography and the latest posts. However, as in the below, when he is blocking me, I cannot see them regardless of visiting to the same URL. Instead, a system message is displayed like you are blocked from. Our key insight here is that the blocking feature enables a user to control the visibility of another user in the same services. Since the content size and server processes are different, the RTT of requests for blocking and non-blocking pages show different distributions. An attacker can use this difference to estimate whether a website visitor is blocked from an account or not. And an attacker can prepare accounts which hold a binary state of blocking or non-blocking with respect to an arbitrary user beforehand. This is a fundamental principle of our attack. That is, the user blocking feature designed to suppress harmful users can now be turned against harmless users to identify their social accounts. Here, I will explain the procedure of the user identification attack. Our attack has two separate phases. The side channel control phase is required just once before performing the attack to construct user identifiable side channel data through user blocking. And the side channel retrieval phase is executed every time a user visits to identify his accounts utilizing the data retrievals through the timing side channel. The side channel control phase has three steps. First, the attacker enumerates accounts on the social web service. These accounts will be the candidate of the visitor's account, so it is better to enumerate more numbers, but for illustration, only 8 accounts are enumerated in this figure. Next, the attacker assigns a bit string, bit array to these accounts from 000 to 111. Attacker prepares as many accounts as the number of digits of the bit string like S1, S2, and S3. We call them signaling account in this research. The blocking state of the signaling account corresponds to each digit of the bit string. That is 0 as non-blocking and 1 as blocking. Note that an attacker needs to prepare only m signaling accounts to cover 2 to the m's power targets. So the target list can easily be scaled up. If an attacker has 32 accounts, it will be able to cover all billions of internet users. Finally, the attacker performs blocking to each target by each signaling account according to the table. Of course, an attacker can automate this task to the best of my knowledge. Most services do not have blocking functions with rate limit and upper limit. I guess this is because it is not common abusing the blocking feature as opposed to friend request and direct message, often used for spamming. So next, the side channel retrieval phase has also 3 steps. First, unknown visits the attacker site evil.com and gets a JavaScript code. He can be guided to evil.com by search engines, mail links, or malicious advertisement. And the JavaScript code forces him to send a request to the profile pages of each signaling account. This is a behavior common to CSAF, but please note that the attacker cannot see the contents of the response because of same origin policy. Instead, the attacker obtains the RTTs of these requests. And finally, RTTs are used to estimate the blocking state. In this figure, a larger RTT is measured in the request for S1 and S3, so they are estimated as a non-block. And a smaller RTT is measured in the request for S2, so it is estimated as a blocking. I will explain the procedure of estimation later. And the attacker can retrieve a bit array from these estimations, a sequence, blocking, non-blocking, and blocking. It means 0, 1, 0, so she's Carol. Okay, here I will show a demo video that simulates each viewpoint of the website of visitor and the attacker. This is an attack setting for the demonstration in this time. The attacker prepares 8 signal accounts from S1 to S8. So this table can cover 256 target accounts in total. It indicates, it includes Takuya's account, that is my name, who visit the attacker's website in this demo scenario. The attacker assigned me a bit pattern of 001, 00011. If I access the profile pages of each signaling account, it will display like these figures. But actually, since a web service does not make a notification when user blocked, I will not notice that I was blocked from the signaling account. So it means that I have no hints to recognize what I was targeted by someone. Okay, this is demo video. Let me first show you my login status because I have login cookie for Twitter now. The top page of Twitter shows my timeline. This picture has no connection with my demo. This is my login state. And I close Twitter and enjoy internet browsing. I access a blog. This blog is a legitimate blog. However, malicious advertisement on the left side, we can consider other attack scenario such as inducing via email or direct message and forum link. Unfortunately, I clicked on this malicious advertisement. Okay. This page displays dummy content. Here, I open the developer tool and check the background behavior. Okay, you can see that I unintentionally request to the profile pages of 8 Signal accounts by JavaScript. It is difficult for a general user to notice these requests, or when a user notices, the attack is over. Okay, finally, let's look at the attacker's point of view. The attacker can measure the RTTs of my request. In the left pane, the graph plotted RTT for signaling accounts are displayed. And in the right pane, the RTT values are displayed. Clearly, you can see that there are gaps between the non-blocking signaling account and blocking accounts, right? Looking at this graph, it is easy to decode the bit array of blocking state that is 001, 0001. Please note an attacker can do it automatically by using statistical method. Finally, the attacker identified that the visitor clicking on the advertisement is Takuya. And this is a JavaScript code snippet that measures an RTT. Despite having the same origin policy, the attacker can get the RTT difference by this code. It just takes the difference between the time before sending some cross-site request and the time after sending it. And per RTT goal and minus start. It measures the required time for the request sent by the image tag. The import source does not need to be an image because we can define on-error event. And we can substitute other tags that can send cross-site requests, such as video tag, iframe, and script tag, but this is an example. This code is not novel. It was proposed in 2007. Of course, the value of RTT depends on the user environment. So in our method, we have prepared two extra accounts. The closed account, which blocks all users included in the list of target, and the open account, which does not block any users at all. This is useful to determine the threshold of RTT. And this is the estimation procedure for the statement of blocking and non-blocking. I will skip the details, but what we are doing is extremely simple. If an RTT for a signaling account is close to the RTT for closed account, it can be said that the signaling account is blocking the visitor. Similarly, if an RTT for a signaling account is close to the RTT for the open account, the signaling account is not blocking the visitor. Since RTT is not stable, the accuracy of the estimation increases by repeating measurements. Our insight is that the accuracy increases by using 50th percentiles of the RTTs for each account. Here, I introduce the two extensions of the attack. The first one is error correlation coding. Our method assigns bit strings for each account, so we can adapt a typical error correlation algorithm. We try the application of the Reed-Solomon code in this work. Another one is user space partitioning. The size of the target list of our attack can be constrained by the maximum blocks of the service. So the target list is enlarged by partitioning the user space and running an additional measurement stage. I put the detailed procedure with our white paper accessible from the Black Hat website. Then we performed field experiments to evaluate the feasibility and impact of our attack. As mentioned above, the success of our attack depends on distinguishability of RTTs. This figure shows RTT distribution on Facebook. The red mark is for blocking, and the black one is for non-blocking. There is a clear gap between the RTT distributions. For some services, please note the RTTs for non-blocking accounts are longer than RTTs for blocking accounts, but which is longer is not important. It can be identified if there is a gap. For each service, we measured the RTTs between blocking and non-blocking accounts. Then we applied the Mann-Whitney U-test and computed the p-values. The Mann-Whitney U-test is a non-parametric statistical test used to compare differences between two independent samples. If the p-value is less than 0.01, we consider it to be distinguishable. As a result, we found that at least 12 popular services are vulnerable to our attack, including SNS, auction, online dating, online gaming, and porn sites. Here I will show the success rate of the attack. First, we conducted experiments to evaluate 1-bit estimation accuracy. We choose especially popular services, Facebook, Twitter, and Tumblr for evaluation. In this table, TBR is the rate of detecting the blocking user as a blocking. And TNBR is the rate of detecting the non-blocking user as a non-blocking. As you can see, the accuracy improves as the number of iterations increases. Blocking and non-blocking state is perfectly estimated by iterating over 3 times on Facebook, 10 times on Twitter, and 20 times on Tumblr. Next, I'll show the result of our experiment conducted in an environment limiting actual attack scenario in the real situation. We use 20 real accounts as target accounts, log in each account, and visit an attacker's website. We assign random 24 bits array, which can cover over 16 million targets. In addition, we applied a Reed-Solomon code with a block length of 4 bits with 8 redundant bits, which enables it to collect 1 block of error. I summarize the number of accounts we prepared in below. And we prepared 3 kinds of connections to show that our attack is established regardless of network conditions. Facebook with wired LAN, Twitter with Wi-Fi, and Tumblr with tethering. The results show that the experiment succeeded with extremely high accuracy. For Facebook wired, there was 1 failure case which identified the target as a wrong user. Examining the network log for this case revealed that some requests to one of the signaling accounts had returned 502 response code due to a temporary server error. Nevertheless, applying the Reed-Solomon, we were successfully able to correct this bit error, which resulted in the success of identification. Next, I will show the time to compare the attack. This figure shows the relationship between the total number of requests and the required time. Also omitted here, the total number of requests can be derived by a simple calculation. For instance, when the number of iterations is 3 that achieves perfect estimation in Facebook, the total number of requests is 132. In this case, the time required is 4 to 8 seconds. Also, when the number of trials is 10 that achieves perfect estimation in Twitter, the total number of requests is 300. In this case, the time required is 12 to 37 seconds. Actually, the required time depends on measured RTT for each environment. This is the result of our experiments. Next, I'll discuss the novelty of our work and applications of this attack. A pioneering work in this field is published in IEEE S&P. They have similar goals, that is, de-anonymize a website visitor. Their approach combines group membership information of users in SNS. It does not require login cookies, but it depends on the history stealing attacks, such as the method of abusing CSS property. To the best of my knowledge, it is no longer feasible in the latest browsers. Our work leverages the user blocking mechanisms, which is perfectly attacker controllable, employs the timing side channel even still available, and demonstrates for the widespread type of web services, SNS, shopping, gaming, dating, and phone sites. We argue that the feature for an attacker to control the visibility of target users enables this attack. This property may be brought by other functions such as friendship, user group, and image sharing. These functions provide limited access privilege to some other users. But still, the user blocking is by far the most practical application, I think. It is factory attacker controllable. It does not notify target users, and it does not require approval action by target users. In addition, user blocking tends not to have any limits. And I discuss our attack for mobile environment. The RTT can be measured even with the mobile browsers. However, users of mobile typically access social web services through dedicated mobile apps. The mobile user may not have a login cookie in the mobile browser. So the mobile attack is established after using social plugin and single sign-on in mobile browsers. Or the access by web view of the dedicated apps may have a login cookie. Here, I will introduce possible defenses and the efforts of us and service providers and browser vendors for responsible disclosure. First, let's explain the typical CSRF defense by verifying a referral or CSRF token. This assumes that requests sent from legitimate pages have legitimate tokens or legitimate referrals. With this measure, requests that came from other third-party sites is dropped. In the case of our attack, RTT is measured by sending a request to the profile pages. Of course, profile pages are often linked directly from the search engine or blog posts or something. So this measure will drop a lot of legitimate access in this attack. Okay, based on that, there are several possible defenses to mitigate our attack. I will introduce some of them. Same-site attribute is I think, most smart solution. That is a cookie option suggested by Google, which prevents the browser from sending the cookie along with cross-site requests. It is effective, but it requires support for both browser and web services. And for web services, the placeholder page is also well-defense technique. The key idea is that the server first returns the page with almost constant content, regardless of blocking state. After that, the actual content is requested with CSRF token or legitimate referral by using XML HTTP request. And the actual content is returned only when the token is validated. It requires a change in the system architecture design, and also the delay caused by the extra session will happen. For users, simple countermeasures, using secret mode or signing out from services or using no scripts. These countermeasures definitely work, but the service providers would rather users not activate these methods because of their marketing and advertisement strategy. A same-site attribute is proposed by Google to prevent the browser from sending the cookie along with cross-site requests. If visitors' browser support it, it is very easy to use. Just add several letters to the set cookie of the HTTP headers. Same-site attribute has two options, lax and strict. Here is an example of lax. Let's consider a case where a website visitor with a cookie for example2.com visit example1.com. If cross-site request is generated by JavaScript from example1.com to example2.com, that cookie will be removed. In other words, the visitor does not have a login cookie state with this cross-site request, so our attack does not work. However, the cookie is not removed if the visitor moves from example1.com to example2.com by link click. This is effective to prevent CSAF, including timing attack, without compromising availability. But at first, browsers other than Chromium did not support the same-site attribute. We reported this attack and possible defenses to service providers impacted by this attack. Here, I introduce a key achievement of our efforts. Twitter's security team have investigated the same site attribute for browsers, supported it, and referral-based defense for other browsers, which prefer is similar to placeholder page. We cooperated with their preliminary experiment and confirmed that the attack no longer works on Twitter. Also, Twitter and us explained the importance of same-site attribute to browser vendors, and now all major browsers supported the same-site attribute. To be honest, I did not expect browser vendors to respond so quickly. I deeply appreciate Twitter's mediation. And several other services are also finished implementing defenses, but we do not have permission to mention their brand names. Okay, let me summarize our work. We presented a practical side channel attack that identifies the social account of a website visitor. It exploits the user blocking mechanism or the visibility control property commonly available in most social web services today. We have successfully addressed this attack by collaborating working with service providers and browser vendors. Finally, I present key takeaways that are useful to social web service users and providers. It should be noted that internet users can be destroyed their anonymity by unexpected ways when using social web services. A feature that enables to control the visibility of other users, like user blocking, can introduce new information leakage channels to attackers. With all of the major browsers adopting the same site attribute, web developers obtained a robust means to prevent CSAF, including side channel attacks. Okay, that's all. Thank you for attention. Thank you.